The capability that we'll be discussing is specific to accurately predicting the battery's state of charge. State of charge, or SOC, refers to the amount of electrical energy that's stored in a battery at a specific point in time, and this is expressed as a percentage of the battery's total capacity. In simple terms, the SOC indicates how full or empty a battery is. SOC is typically determined by measuring the battery's voltage, current, or a combination of both. However, accurately estimating the SOC can be a challenging task due to factors such as aging, temperature variations, and non-linear behaviors. Electra innovated from state-of-the-art research in machine learning and AI algorithms and adapted modern technologies in ways that are not typically expected. The adaptive cell modeling system is a conglomeration of many software components that complete specific tasks, like analyzing physics-based battery modeling workflows, data science analysis, and machine learning and AI operations on BMS sensor data. The Electra adaptive cell modeling system is first informed by laboratory tests, which focuses on the degradation of the specific battery that we're looking to model. This allows us to create a baseline of the battery's internal state at the beginning of its life, and we need this data to create a physics model, which will then be used to teach the machine learning and AI model. This is often referred to as physics-informed or simulation-informed machine learning. Once we have a detailed overview of the real-world battery in the lab, transcribed as simulated data, we then train the AI algorithm to understand the complex relationships that exist between the many various data points that are collected when the battery is in operation. There is an art in how we combine information from the simulation with the machine learning model in order to predict specific future states, like state of charge. Electra's team of battery experts have spent years putting the pieces together to predict accurate future states of various types of battery cells. To handle the pack data, there are also components in ACMS that manage how the raw BMS sensor data is broken down in the cell level data, which is then used by the system, and how the decomposed cell level data will be recomposed in the pack level data. This all comes with some overhead for how this data is formatted, written, and read. Ultimately, the information that's produced by the BMS and also ACMS components are all used to prepare a twin model of the battery pack. This model is automatically deployed onto the battery pack, which means that the battery pack will get a model update and the predictions of the state of charge immediately become more accurate and more precise. The Electra ACMS also has several key features that separate it from the existing methodologies. First, it's a cloud-based solution that's integrated with advanced NXP hardware. And this is very different than the typical methods that don't have cloud connectivity or processing capabilities. Second, ACMS uses a scalable framework, meaning that it can accommodate a huge number of battery packs automatically. Third, it supports real-time data acquisition and a time series data storage system in the cloud. Typically, this data isn't saved because of the processing and memory limitations on typical BMS systems. But this data allows our internal battery modeling team to develop algorithms and monitor the pack.